Hello friends. So today we are going to discuss 4 questions, and these 4 questions are from rotational motion. And so the first question, it states that, one second. Okay, so this question, it states that consider a simple rigid body composed of 2 particles, each of mass m, connected by a massless rod of length 2L. The midpoint of the rod is attached to a vertical axis that rotates with the angular speed omega about the z-axis. The rod is inclined at an angle alpha with respect to the vertical as shown in the figure. I'll draw later on. Determine the angular momentum and the torque of the system. So we are given that we are having 2 particles, each of mass m, and these particles are, you can say, connected by a rod whose length is given as 2L. So let us suppose this is our rod and we are having 2 particles, each of mass m, and it is said that, suppose this is our vertical axis and it has to be symmetric about that. So let me draw, so somewhere here, and it is attached to a vertical axis, and that vertical axis is making angle of alpha about our vertical. So this is our z-axis and we are having alpha angle here. And okay, so in this case we have to find out what will be the, you can say, our angular velocity of our angular momentum and the torque of the system. So in this case we have to remember that the entire system is moving or rotating about z-axis, and let us suppose with the angular speed of omega, and because of that this both m is masses is going to rotate in some kind of your circular motion individually. So this is the basic question given to us, and so first of all we try to understand the geometry of our this system, and for that let me draw this separately. So we are having a mass m at each end, and let us suppose this point is called as our O, and total length is our 2L. So the distance of this O is L from both the masses. Okay. And the circle which they are going to form with our when the radius of circular motion is, let us suppose we call this as our R, and therefore so this is our R, and symmetrically on the other side we are going to have this as also our R. So we can say that geometry of the rod. Geometry of the rod. And this geometry of the rod, like I said, that our distance of each mass from the midpoint is our L. So we have our distance of each mass from the midpoint, and midpoint we have taken as O, and that is equal to our L. Therefore we can say that radius of the circular motion, if that is taken as our R, then this R will be equal to our L sine of alpha. Okay, that is basic. And we can also find out the vertical component of the position along our z axis. Therefore we can also say that vertical component of position along z axis, and that will be equal to our L cos of alpha. And so it means each mass is going to move in a horizontal circle of radius R, which is our L sine of alpha. So from, let me rephrase it, or we can just use it as it is. And next is we are going to find out the moment of inertia about z axis. Moment of inertia about z axis. And we know that for a point mass, the standard formula for moment of inertia is equal to mr square. Okay. And our so each mass is at a distance of L sine of alpha. So we can say that our for point mass, moment of inertia is equal to mr square, and each mass is at a distance of r from our z-axis. So we substitute value of r, which comes as our m, and r is our L sine of alpha. Therefore from here we get that our moment of inertia, and that is about our z-axis, so let us call this as I of z. So we get, and okay, in this case we have two masses and they are symmetrical. Therefore let me call this as Iz. So I can say that my Iz will be equal to first mass plus second mass, which will be coming as 2mr square, and now we can just substitute the value. So we get this as about 2 times m, and our r is our L sine of alpha whole square, and we get that our I of z will be equal to 2m L square, and this is our sine square alpha. And from here we can find out our angular momentum, because we are supposed to find out the omega. So we can say that our angular momentum and so we have our angular momentum of the point mass angular momentum of point mass let us call this as our h. So we can say that our h will be equal to r, and we have this as our m v vector, and we can easily substitute our v. So we get this as our m, we can take as common, so this comes as m, and we have our this as r vector, and omega, because v is equal to nothing but omega our r. Okay. And we can divide, or we can say decompose the omega along the rod and perpendicular to the rod. So we can say that decomposing omega into its component, and we are going to have two components. First component will be our along the rod, and along the rod let us call this as omega parallel, which will be equal to over omega cos of alpha. And next is our perpendicular, so you can say perpendicular to the rod, and perpendicular rod we can say this omega perpendicular will be equal to omega sine of alpha. And obviously for the contribution of the angular momentum, only the perpendicular component is going to contribute to the angular momentum. The parallel one is not going to support it. And so from here we can say that only perpendicular component contributes to angular momentum. To angular momentum, because quite obvious the parallel will be in the passing through the axis which is through the mass. Okay, so that's why the parallel is not going to contribute towards our angular momentum, only our perpendicular is going to contribute. Therefore, we can say that our h of z will be equal to our I of z times omega. And we can write this as our 2m I of z we calculated 2ml square sine square alpha and times omega. Therefore, we can say that our total angular momentum will be equal to, and with respect to their components we can write this as our h, and so we can say that our h will be equal to, we have this as 2m L square, and this will be giving us sine and cos, so we are going to get this as our cos square alpha k unit vector minus sine alpha cos alpha and I unit vector, and we can just solve this part because we are only interested in the magnitude. Therefore, we can say that let us call this as h prime, then we can later on substitute it. So we get h prime, its magnitude will be equal to, we have our cos square, and cos square is going to give us one second. Okay, so we are having this as this will be our cos square, giving us cos 4 alpha and minus sine alpha cos alpha, that will be coming as plus sine square alpha cos square alpha and its square root. In this case, we can take cos square as common, so we get this as our cos square alpha, and that will be equal to cos square alpha plus sine square alpha and its square root. And this cos square plus sine square is 1, so we get our h prime magnitude is equal to cos of alpha. Therefore, our magnitude is equal to, we have 2 ml square, and this is our omega cos of alpha. This is our the angular momentum, total angular momentum that was asked for. And we can also find out the torque. No doubt it was not asked for, but still we can, one second. There is some problem. No, it's working. Yeah, it's working. And we can also find out the torque, and we can say the torque required for steady rotation. Torque required for steady rotation, and that is suppose denoted as m. So we can say that our m and m will be equal to our derivative of our angular with respect to time, or which we can also write as omega and our h. And so if we use the cross product for the rotation about z axis, cross product for rotation about z axis, we get that our m will be equal to, this will be coming as our its derivative, so we are going to have this as minus 2 ml square minus 2m omega square L square, and we have sine of alpha, cos of alpha, and j unit vector. And magnitude, it's quite simple from here, so we get our magnitude will be equal to 2m omega square L square sine of alpha and cos of alpha, and this is going to act perpendicular to both, to our h as well as omega. From this relationship, because of the cross product, we can easily see it. And so in this case, let me solve this in a little bit of detailed manner. And for that, we start with our h, that our h is our 2m L square and omega cos of alpha, and the formula for our torque that we denoted as m is our cross product of with respect to our h, and this can be written as our wh sine of theta, where the theta is the angle between omega as well as our h. And so we are going to find out the value of our theta. So we can say that angle between our omega and h, angle between omega and h, which we are denoted as our theta. So we know that our this angular velocity omega, it points along the rotation axis, which is our z axis. So we know that our angular velocity is omega. It points along our rotation axis, that is our z axis. And we can make two components, or we can say components of our angular momentum. So we can say that angular momentum h components, and we can say that our h, one component will be in our x direction and other one will be over in z direction. So we can substitute and get this as our h of x will be equal to our minus 2m L square omega, and this is our sine of alpha cos of alpha I unit vector plus 2m L square and omega, and this is our cos square alpha and our k unit vector, and our theta is the angle between omega as well as our h. So you can say that our sine of theta will be given as the x component and our h and its magnitude, and we have our 2m L square omega sine of alpha cos of alpha, and 2m L square cos of alpha. So here the terms are going to, one thing, this is cos ml square, and one thing is missing, that is our omega. So this comes equal to our sine of alpha. Okay. And we substitute in the magnitude part, so we get our m is equal to omega, and we have this as 2m L square omega cos of alpha, and sine of theta is our equal to sine of alpha. So this is multiplied by sine of alpha. So this is our torque. And if required, we can also find out the rotational kinetic energy. So we have rotational kinetic energy, and let us suppose that is denoted as T, then T will be equal to half moment of inertia about our Z, and we have this as omega square. Okay. So we simply substitute our I of Z, we get T is equal to half, and I of Z is our 2m L square omega, and one second, I of Z is 2m L square sine square alpha, there is no omega. 2m L square sine square alpha times omega square, and here 2 and 2 cancels out, therefore we get that rotational kinetic energy is equal to ml square omega square sine square alpha. So this is our first question. We come to the second question, and the second question, it states that consider a dumbbell consisting of two uniform spheres, each of mass capital M and radius b, connected by a thin massless rod. The distance between the centers of the sphere is 2L. The dumbbell rotates about an axis through its center of mass. At a particular instant, the rod lies along z-axis. The angular velocity vector in the yz plane is given as omega is equal to y of x j unit vector plus y of omega of z k unit vector. And find the instantaneous angular momentum L of the dumbbell at that instant. Okay. So we have given a particular instant, and that instant states that a rod is along our z-axis, and during that the angular velocity is in yz plane, and its equation is given to us. So we can just draw the approximate figure for that, and let us draw first of all our the axis. So this is y, z, and we have our x. Okay. And we have two dumbbells consisting of two spheres. So let us suppose this is a sphere 1 and this is our sphere 2, and they are connected by a rod. and the rod length is given to us as our 2L. Okay. So this is our, we consider this as a center of mass. So this point is our center of mass, and this value of omega is given as omega y. So we are going to have a component omega y, and we are going to have another component that is omega z. So obviously its resultant will be in, this will be our omega. So this is the basic question, and we are supposed to find out this, the angular momentum. Now this question we can do two ways. The first way we can use, you can say, the tensor or matrix version of our that parallel axis theorem. Okay. And then in the second part we can use our standard procedure, that is our using our conservation as well as the angular or energy. So first of all, let us try to understand that our theorem of parallel axis, and in general which we study, that our, which we can call as, we can also call that as a simpler version of parallel axis theorem. Okay. Or we can say the scalar parallel axis theorem. And which we can write that moment of inertia of our I naught will be equal to moment of inertia of the body about its center of mass plus mass of the body and the distance, that is our d square, perpendicular distance, and here m is the total mass. Okay. And this is for our single axis. But if in 3D we can modify this equation, so we can say for 3-dimensional, because the spheres are nothing but our 3-dimensional bodies. Okay, so we are supposed to use that in a different way. So we can say for 3D, the rotation can happen in any arbitrary direction. In any arbitrary direction. Okay. Therefore, we are going to use this parallel axis theorem, but that parallel axis theorem is called as a tensor version, or it is also called as a matrix version. Tensor or our matrix version, and that is our I naught is equal to ICM plus mass, and we have this as our d square times I minus d and d. So this is called as a parallel axis theorem for tensors. And now let us solve the question based on this theorem. Then in the second part, or we can use the more traditional way which we are used to. So like we said, that the total length is given as 2L, and here we can say one end is our plus L and the other end is going to have our length as minus L. This is our origin. So we can say that our center of mass is of origin. Center of mass is considered at origin, and it is given the question that at this particular instant our rod coincides with the z-axis. Okay. So for every solution we are going to consider that picture which I have already drawn also. And the angular velocity is also given to us for that particular instant is our omega of x, omega of x, omega of y. Omega of y j unit vector and omega of z k unit vector. So first of all we are going to find out the moment of inertia of the sphere about its own center. We can say that moment of inertia of sphere about its own center, and let us call this as our I sphere with respect to its own center, and that will be equal to 2 by 5 mb square. And now we are going to use the parallel axis theorem, or we can say the tensor theorem. And for that we can say that parallel axis theorem, and for that we move each sphere inertia to the origin and we know that the sphere, its center is, distance is our d, and we know that sphere center is given as 0, 0 plus minus d, plus minus L, and this is nothing but our d. So now we can use that our moment of inertia of our sphere with respect to origin will be equal to moment of inertia of our sphere with respect to our center, and plus, one second, I missed something, no, plus m, and we have this as our d square I minus d of d, and our d square will be equal to our L square, and this d of d, it is only going to have our zz component. So we have only having zz component. L square, and Therefore, we can say that our I sphere with respect to origin will be equal to, and we can write this as our in the format of diagonal, and that is going to give us our IC plus ml square comma IC plus ml square and our IC, and IC is nothing but sphere with respect to our center, which we already know. Therefore, and we are having two identical spheres, therefore we can say that our I total will be equal to, this comes as our diagonal and 2 times IC plus ml square, 2 times IC plus ml square and 2 times IC, and IC is our 2 by 5 MB square. Therefore, we get that our x-axis will be equal to our y-axis, and that will be equal to our IC is 2 by 5 MB square and plus ml square multiplied by 2, and our z-axis will be giving us 2 times of our IC, which is our 2 by 5 MB square. So from here we get this as our 4 by 5 MB square plus 2 ml square, and this was our Ix, y, and we have our Iz is 4 by 5 MB square, and we know that our angular momentum is our L, which is our I times omega, and in terms of the respective axis we can write this as our I y and omega y j unit plus I z and omega z k unit. We simply substitute their values because we know our y and z. Therefore, we get that our angular momentum will be equal to 4 by 5 MB square plus twice ml square and omega y j unit vector, and we have this as 4 by 5 MB square and this is k unit vector. Now in second pass, because this looks somewhat complicated and we can solve this also using the method, and in this second approach we are going to use the spring angular momentum in which spin angular momentum, in which the sphere will be rotating about its own axis, and then we are going to use the orbital angular momentum, and that orbital angular momentum will be about our, you can say, the center of mass, which is that required thing. So we can solve it by, we are going to get the same result but with different approach, and that approach is much more intuitive and is going to give us, you can say, more result which we are more familiar with. Okay, because here the theorem, parallel axis theorem, is nothing but the extended version of the parallel axis theorem. So in the second approach, in this second method, we are going to use the spin angular momentum, which is basically the sphere about its own center. Sphere about its own center, and this is our first one. And the second one, we are going to use the orbital angular momentum, and this orbital angular momentum we are going to the spheres about the center of mass, about the origin. So in this case we are going to use the momentum of orbital angular momentum of spheres center of mass about the origin. Okay. So let us sort it out. So first of all, let's find out the spin angular momentum of both the spheres, and we know that the sphere center they are the distance r, and that is equal to plus minus L and a k unit vector, and also we are given the angular velocity which is given as omega, and that omega is equal to over, we don't have its x component, we are only having the y component as well as our z component, and we are given that the moment of inertia of our spheres with its own center, that is our, we are not given but we know 2 by 5, and this is our m b square. So let us solve for it our spin angular momentum. So we have our spin angular momentum, and that we can say is our L, and that is our spin, and we are going to find out the first one, only one, and that is equal to our formula is quite standard, that is our IC multiplied by omega, and we are having two spheres, so we can say for two spheres spheres, let us call this as L spin, and total will be equal to twice IC times omega. And from here we can write that our L spin, our total will be equal to, we can write this in the form of the coordinate. So we are going to have this as 0, because coordinate of omega doesn't have x component. So this is our 0, and this is our 2IC omega of y and 2IC omega of z. Now we find out the orbital angular momentum. Orbital angular momentum. And for that we know that our linear speed, that's our v, will be equal to omega cross r. So we can say that velocity of sphere center velocity of a sphere's center, that is our v, is our omega r. Therefore we can write that the orbital angular momentum for one sphere, let us call this as L orbital 1, will be equal to our r cross mv, and v already we know, so we can take m outside, so this comes as r, and this is our omega and r. Okay, so this is a triple product, and so we have our sphere. Let us suppose one sphere, and that we are taking it as a positive L. So you can say, so for plus L sphere, we can say that our L orbital 1, and triple is because we know that for this we are going to have r is equal to our plus L k unit vector, and the identity for this triple solution is our r dot r multiplied by omega minus r dot omega multiplied by r. So r dot r will be our L square, and our r dot omega will be equal to our L omega z, and this is our times r. One second. Okay, so we can substitute it, and we get our L orbital for 1 will be equal to our m, and we have this as our L square omega, and this is our minus, and L wz, and our r is nothing but our L k unit vector. So we can further write it as our m, and we have this as L square omega minus this will be over L square omega z k unit vector. And we know that our omega is our 0 comma omega y and omega z. Therefore we get the L orbital for only one sphere will be equal to, this will be over 0 comma, we have this as m L square omega of y and comma, this is our z and z, so this will be coming as our 0. And for the other sphere means we are going to take r is equal to minus L k unit vector, and for that the result will be same magnitude. Okay, and therefore for total we can just write it's their summation. Okay. So we can say that our L orbital total will be equal to twice of L orbital 1, so which gives us twice m L square and omega of y j unit vector, or we can also write this as 0 comma twice m L square omega y comma 0. Now the total angular momentum will be the orbital plus the spin. So you can say our total angular momentum, which is L, will be equal to our L spin total plus L orbital total. And we know that our I of C is our one second, I think I missed something. No. And okay, so we can say that our L, and we know that our I of C is equal to 2 by 5 mb square. Okay, one thing that was not mentioned in the calculation is our I of C. Okay, we simply multiply it here. So we get this as our L orbital plus L spin. So L orbital is a 0 and L spin is also our 0. So this comes as 0 plus 0 will be equal to 0. So where this is 0 comma, and this will be twice IC omega of y plus twice m L square omega of y and this is 0 and upper part is our twice IC omega z, twice IC omega z. So we substitute, we get our L is equal to IC, we put and we can just add them. So we get this as our 4 upon 5 mb square plus twice ml square omega of y, and we can, this is j unit vector plus 4 by 5 mb square multiplied by omega of z k unit vector. So we got the answer by, we got the same answer by using the, you can say, the second approach. And second approach is much more understandable, because here we are not going to use any of that particular theorem. Okay. And next question we are going to use for the next question. We are given, sorry, got lost. And so in this question we are given a thin loop of mass m and radius r rolls without slipping about z-axis. It is supported by an axle of length r passing through its center as shown. The hoop moves in a circle around z-axis with a constant angular speed omega. And we are supposed to find out two things. Determine the instantaneous angular velocity omega of the hoop. Find the angular momentum L of the hoop is L parallel to omega. And we are given that the moment of inertia of the hoop about the diameter is mr square upon 2. And we can just draw the figure. We are given that we are having a z-axis and y-axis, and this is our x-axis. Okay, and this hoop is moving in a circular orbit along z-axis, and we can just draw the hoop that will be coming something like this. And this hoop is at a distance which is given to connected by an axle of length r. So suppose this is the center and it is connected by a rod. Okay. So this is our hoop. Which is something like a cycle tire. And its radius is given as r and the axle distance is also given as r. So obviously the circle with which it is going to rotate about z-axis is also going to have r. And it is a constant angular speed omega. Okay, so it is moving with the angular speed of omega, rotating about z-axis with the angular speed of omega. So there will be two types of, or we can say they are going to have spin angular velocity, and then is going to have it as angular velocity which is with respect to z-axis. So we have write it in two ways. I think so in order to differentiate, we have to, okay, we can use a separate notation. So let us solve our part A, instantaneous angular velocity, that is our omega. So we have our part A, and so in this case we can say that our rolling without slipping if we assume that the speed here is our v, and we can say that it's for rolling without slipping, the linear speed relative to the center. The rim linear speed relative to center, and that will be equal to our W spin times R, and that will be equal to, that is our velocity of the center. So we can say that the velocity of the center VCM, and that is equal to over omega times R. So these two velocities should be same, therefore we can write that our omega spin times R is equal to omega times R. So here this R and R cancels out, so we get this as omega spin is equal to our omega, and its direction will be along our x unit vector, and this hoop is also carried along the z-axis at a rate of omega. Therefore we can say the angular velocity will be equal to its omega, which we have already denoted. So we are also given that the whole hoop is, or we can say whole hoop rotates around the z-axis and the velocity is our omega, and it will be our z unit vector. So therefore we get the total, what was asking for, part A is instantaneous angular velocity. We can say that instantaneous angular velocity omega will be equal to our omega x unit vector and omega z unit vector, or we can say that our omega is equal to omega, and we have this as our x unit vector plus z unit vector. So this is our first part, and second part we are supposed to find out the angular momentum of the hoop, and the angular momentum of the hoop will be about the center is our, it is given to us about the diameter, and for y is our rotating in a, you can say I of y as well as I of z will be equal to half mr square. So part B, and we can find out the angular momentum of the hoop's center. Angular momentum about hoop's center, and omega we already know, so we can say that our I of x is our mr square, and I of y as well as I of z will be equal to our half mr square. So we get the angular momentum about the hoop's center will be equal to I of x multiplied by omega of x, x unit vector, plus I of z, omega of z, and we have this as z unit vector. So we simply substitute the values, we get this as our mr square omega x unit vector plus 1 by 2 mr square omega z unit vector. And now we are going to use parallel axis theorem to find out angular momentum about the origin. Angular momentum about origin, and for parallel axis theorem we can write angular momentum about origin will be equal to angular momentum about its center plus r, and we have this as m multiplied by velocity of our center. And so let us calculate this part. So we have our r and our velocity of our center. So r is our r x unit vector, and velocity of center is our m omega r y unit vector. So this gives us m omega r square, and cross product is our z unit vector. So we get our L origin L center we already know is our m r square omega x unit vector plus, and we have here this is also z and this is also z unit vector, so we can just take it common. So this comes as our half m r square omega plus m r square omega and z unit vector, and we can add these two terms. So we get this as our m r square omega, and we have x unit vector plus, this will be coming as 3/2 m r square omega z unit vector. So this is our angular momentum about the origin. And here it is asked that is L parallel to omega, and we know that our omega in terms of their directional component, we can write that omega is proportional to our 1, 0, 1, and our L is proportional to our 1, 0, 3/2. And from here we can say that they are having different components. Therefore, we can say that L is not parallel to omega. They have the different directional components. So these were the two things, and we come to the next question. And it states that a flywheel with a moment of inertia I naught rotates with angular speed omega naught, angular velocity omega naught at the middle of the axis of the length 2L. Each end of the axis is attached to a support by a spring, which is stretched to a length L and provide tension T. You may assume that T remains constant for the small displacement of the axle. The supports are fixed to a table that rotates at a constant angular speed omega, where this omega is much smaller than omega naught. The center of the mass of the flywheel is directly above the center of rotation of the table. Neglect gravity. Assume that motion is completely uniform. Find the direction of the axle with respect to the straight line connecting the two supports. So first of all, let's draw the approximate figure. So we are given that there is a table, and on which we have connected this entire system. So we can just draw a table, and there are two supports, and let me so we have two supports. One support is here and the other support is here. And there is a disc. These support are connected with a spring to the other side also, and there is a disc which is connecting in between like this, and it is connected to the spring. And this table is rotating with the speed of omega, and this disc is also rotating with the speed of omega naught. And we are given that the spring is having a length of L, So this distance is said to be over 2L, and the spring distance is said to be over L on the either side. Okay, so obviously this disc which is connected with the support is going to rotate, and if it is going to rotate, it will be giving some twist to it, and because of the turning of the table, there will be certain, you can say, change in the position of this disc with respect to the springs. We will draw that later on also. And so let us write the things which are given to us. So first thing we can say that the flywheel moment of inertia about its axle. Okay, so this is the axle, the line which is connecting the spring. So we can say moment of inertia of flywheel about its axle. Let us call this as our I naught, and the axle length is given to us as 2L. So we are given that we have the axle length which is our 2L, and also we are given that it is attached to the spring, and let us assume that the tension in the spring is given as T. So we are having T tension in this spring. So we can say that the spring tension is T. Is our T, and we assume that this axle tilts by a small angle phi relative to the line connecting to the supports. Okay. This is the important part here, because we are going to find out this phi, okay, which is because we are going to find out equilibrium tilt angle, that is our phi. So we can say that the axle tilts by a small angle phi, tilts by a small angle phi relative to a line connecting the supports. Connecting the supports. And so we are going to use this small angle approximation also, and let us try to understand this small angle with respect to angle phi. So we can draw this figure from the front part also. So this is the base, suppose, and we are having the supports, and the disc is somewhere here, and this is our axle. and it is connected with the help of the spring. To the supports. Something like this. And we are given that the L is the length here as well as on the other side, and 2L is the length of this. So let us call this as A, B, C and D. And there will be tension T on this side as well as on the other side also. So this is our basic figure. And we can just draw our phi also, and that phi this is our axle, and the original position of the, let us call this as our horizontal here, and here also horizontal part, and the springs are one in this direction and other one in this direction. And this twist is, we can just extend this a little bit so we can draw the angle phi. So we are going to get that our angle phi will be this and this, and we can just join these two parts, and we know that this length is our L because the total is given as our 2L, so with respect to the center of mass, and this will be also our L. So this is our the figure which is given to us, and from here we can find out our what will be our, this is our point B and this is our point C. So we can find out our x component, sorry, one second, this is not L, my mistake. L is the length, this as well as this. Okay. So we can find out the x component of our B and x component of a C, and also we are going to find out y component of B as well as y component of C. That is basically our using the trigonometric identity. So we can write that our x of B will be equal to L cos of phi. So this is our x of B, x component, and this is our x of C, and this will be our y of B, and this will be our y of C. And from small angle approximation we can say that x of B is approximately equal to our L. Similarly, we can write our x of C will be equal to L cos of phi, that will be also equal to our L. And Then we can find out our y of b. So we get our y of b will be equal to L sine of phi. This will be giving us L of phi, and we have our y of c will be equal to our minus L sine of phi, that is minus of L phi. So we are only interested in this our y, because x is not so much of important to us. So we got the values, and you can write and here center of mass we have taken as origin. So x of b will be our basically minus, and y of c will be also minus, okay, because center of mass is our origin. So we got the y coordinate and x coordinate. So now we can say that the horizontal displacement relative to the center, horizontal displacement relative to the center. And that will be equal to our y of b minus y of c relative to the center, and this will be equal to our y of b minus y of c, which will be giving us L of phi minus of L of phi is equal to twice L of phi. And the torque for each spring will be equal to force multiplied by lever arm. Okay, lever arm is nothing but perpendicular, which we just found out, 2L of phi. And you can say that our torque for each spring let us call this as tau s, will be equal to force multiplied by lever arm. Force is our tension, so we get this as tau of s is equal to tension multiplied by 2L of phi. So we have two springs, therefore we can say that tau total will be equal to 2 times tau for the spring, and this comes as our 4TL of phi. Now we are going to find out what will be the effective reaction from the spinning of the flywheel, because the flywheel is also spinning. So we can say that flywheel spins about its axis with angular speed of omega naught. Flywheel spins about the axle with omega naught. Okay, and we have a rotating frame of the table also. So we can say the rotating frame of the table, and it rotates with the angular speed of omega, and this axle, because of the spring, is going to resist the rotation. Okay. And so we can say the reaction force, we can find also the torque reaction, like we find out the torque total. So we can say the ends of axle tends to resist rotation and this can be treated as effective horizontal torque acting on the axle, treated as effective horizontal torque acting on axle. And we are going to call this as our tau reaction, which will be equal to our its moment of inertia, omega naught and omega, because we know that the angular momentum of the magnitude of the spring, this flywheel, will be our I naught multiplied by omega, and the frame is rotating about its the angular, that is our omega. So therefore we can find out its the rate of change of the angular momentum, but anyways that is not required. And under equilibrium, the spring resisting torque will be equal to the reaction torque from the spinning flywheel. So we can say our torque balance at equilibrium, and we can say our tau reaction is equal to tau total. You can say that our tau reaction is equal to tau total. So we substitute it, we get this as our tau reaction is our I naught omega naught times omega, and tau total is our 4t L phi, and from here we get that our phi is equal to I naught omega divided by 4LT. So this is our small angle. So these were the 4 questions which we solved for our using the rotation motion. And so this completes all the 4 questions. Thank you.